certain grave dug in 1771, the grave of an ancestor named Joseph Curwen, some of whose papers he professed to have found behind the paneling of a very old house in Olney Court on Stampers Hill, which...
Alright, so we've got Viraldo. Okay. This is basically a voxel renderer that is also capable of it produces a voxel model and then displays it. So this is the top level class. This is how things are instantiated. If you wanted to put this into main here, I have a pointer to a main block here. Then in main I just instantiate one. Now, yeah, so these are used to initialize it. This isn't fully set up yet. I'm still working on getting it, all the code written. This is the 5th version. Some of the older versions I have on GitHub here. I do have some videos and stuff, but this was, I guess this isn't a very good way to look at that. Here's a better one. This is what this took a number of minutes. I think it was close to half an hour. Rendering separate frames, but yeah. So there's some rotation, and I'm also doing some vector math to rotate the model there. So that's yeah, that's the idea anyway. So Viraldo here keeps the x dimension, the y dimension, the z dimension as integers. Number of cells is just those multiplied. This class got really big, kind of big. Anyway, started breaking it up into subclasses. So now I have a draw class and an IO class, and that's not that fleshed. It's pretty much a container for the display function right now. This data is the array that holds the whole thing. It's one-dimensional. I have a mapping so that I am able to get away from having 3-dimensional arrays. And then I have a palette that allows me to use an unsigned character to represent the color of any given voxel. So it's just 1 byte. So it doesn't get too crazy huge as fast. Anyway, I do keep a boolean also for a mask value, but I'll get to that in a minute. These get and set values. I actually dropped this translation thing and I actually just built it into the get and set data thing, so you basically don't even know that you're not referring to it directly by a vector index. It references the one-dimensional array using this mapping. You have the one-dimensional array index equals the third term rather, index plus y dimension times z dimension. And the second term of the index times the x dimension, and then the first term of the, yeah. So basically that's just how I have it mapped into the one-dimensional array. Now, first is the Viraldo IO class. That's this took a little bit of finagling, but I did get it working. I had to do some forward declaration. of that class. It's somewhat circular, but I like it because it allows it access potentially across between. I think it's an interesting architecture, and I could add more units like the IO and the draw, and they're able to refer back to the data in the top level class, and also the palette and anything else that they need, and through here they could access the other things too. So right now, load and save are placeholders. I don't have a good file format. I was messing with some JSON to try and represent it, but that ended up becoming, not that practical. Basically, I don't know, the text files get kind of big. They're kind of silly, so keep them that way. I want to try and use maybe images or something, just a really wide PNG, basically, or really tall. I don't know. There's going to be more experimentation there, but the display function, that's where most of the interesting ideas I've actually implemented here this time through have come from. Let me show you kind of what we're looking at here. Kind of draw something. You have your block here. Okay, I'm gonna go ahead and I don't have my pen right now. Otherwise, I would do something a little bit less shitty, I guess. So anyway, we've got the block here, right? Well, that block kind of resides within a sphere. You could think of it this way, anyway. A sphere where all of the it touches, every corner touches the sphere, basically. Now, that has a certain radius, and that's based on the size of the cube. Okay. And this is where all the voxels are. So you imagine, divisions here for the z-axis, divisions here, and then obviously in this direction also. I really can't use a trackpad to do this very well, but anyway, so that circle has a certain radius. Well, then I multiply it by 1.3 or 1.7. I don't remember exactly what it is, but this gets me farther away from the cube. Okay. From that point, I basically say, alright, well, that's a distance away from the thing. Now I can say I want, alright, this is a little abstract. I'm going to do another picture here. So, here we are. We're talking about how the camera works. Okay. So it has a position in space that we're starting from. It has a direction that we're looking in. It has an up. And it has a right hand arrow, or left hand arrow. I forget exactly how we're representing it. I have to rewrite it. I've put this down for a couple of weeks because I was having trouble with one little piece of it. I needed to take some time away from it. But anyway, the general notion is here we've got a right and an up, or left and an up, whatever. And I'm going to go ahead and form a grid here that's based upon this origin plus incremental additions of these two vectors. So I end up, every grid reference here, that maps to a pixel on your screen, and it also maps to a point in three-dimensional space then. Now, how do I get this point? And how do I get these points, these vectors, right? Well, I'm glad you asked. So, basically, so if you kind of look at, I guess maybe that's not what I meant. So you have X, Y, and Z, and is that right? X, no, whatever. X, Y, Z. Okay, that's the origin of the space where the voxel block lies. Okay, and that's at one corner of this cube. All right, so we have this X, Y, Z. Okay, and that's butted up against the corner. I'm just drawing it there for emphasis. And so this extends along the x-axis, or the y-axis, or the z-axis, whichever it is. This is really not to scale or logically, necessarily the proper direction, so I'm just kind of drawing it the way I'm here. Now, if I want to then generate these, I'm going to rotate them. I have some, just some matrix multiplication to do to rotate each of these vectors about the x, y, and z axes as you want to do. So you have then these in space. Then what I do is, to get this position, I take the origin and then I add a certain number of times this distance, this vector here that goes in the direction of the camera. So basically, then the origin for display space is down here, down some multiple of this vector. Okay, so then the cube kind of lies here. No, sorry, it's not based on the origin of display space. It's actually based on the middle of the cube. So there's this point that's the farthest extent, and then I kind of divide by 2 and I get the middle. So figure the cube extends down this way and all that. Alright, so I have these points in space, I have a direction, that's it. I do an orthogonal rendering where each one of these points in exactly the same direction. There's no deflection based on like a perspective kind of correction, but I could do that using these vectors for up and right. The same way I'd displace them to the side here, I would just displace the direction vector in the same way, and that would you'd start to get some divergence between these. They would, instead of being parallel lines towards the block, you'd start to see some distance effects. So anyway, as you come down here into the block, you say, alright, what's at that point? As I'm continuing along this vector, I have a number of points that I hit, and I'm going to test the block at each one of those. And that's just using the get and set functions here. It's pretty trivial. Now, if you do that, they have input validation too, so if you use negative numbers or numbers outside of the block, it's not a big deal. It's actually in here. Like I said, I'm re-implementing this now, so it's in pieces, but so like I said, I do a check to see if they're valid, and then return it, and we'll get to the representation of that voxel block. But yeah, the set functions are exactly the same, except it takes into account whether or not the block is masked, and if it is, then you're not allowed to draw to it. I'll discuss that in a little bit here too. We'll get to that too. So basically, when I want to call the display function within the IO class, I don't want to be checking in empty space. Okay, so if I'm out here, I'm doing a very dense number of samples that are like totally irrelevant. They're not even inside the block, so why even check them? Even if you do take that sample, you're just running the validation code. You're not actually sampling the block because you're outside of the block. It's just inherent there. So fuck it. Don't sample there, right? Big optimization. Literally speeds it up 10 times. It's like serious how much it sped it up. So that's this intersection of a array and a bounding box. So I have 0, 0, 0. That's where the origin of the display space is. That's here. Then this point, which is here, that's the maximum extents along each axis. Then I have array direction, or array origin and array direction, T0 and T1, and Tmin and Tmax. Now, if you're familiar with the parametric form of a line, basically you start at your origin point. So you're here, that's your origin point, and you have your direction. Well, to step along it, you're going to do, t equals 0, you're here, because you're at the origin, and your position is origin plus t times direction. So you're just at the original position. Well, then as you add 1 times, so you've got t equals 1. Well, then you've actually moved in space. You're here now. That's no longer the same position. So basically, as you extend that, you get to 2 and 3 and 4 and 5 and 6, and you continue on into space. You can do it until t equals infinity. You could do t as a negative number and move this way. So the real takeaway here is, at some point, you're going to intersect this box and leave this box. Okay? And we want to know what t is here. We want to know what t is here. We don't want to know if there are no values of t that allow it to hit the block. Say if we start out here and are going this way, we never touch the block. So that's significant. And I'm not really considering cases in which we get 1 point. I'm really just treating that as, an unnecessary complication. I actually really like the low fidelity kind of like weirdness that you get, the artifacts that you get from the sampling. I actually like how chunky they look. They're kind of a big part of what attracts me to this. I can kind of show you what I mean here. like in here, these are just voxel artifacts, but I don't know. The only real ambiguous ones are at the edge sometimes. But basically, as you sample through here, you see there's a close intersection point at this red edge, and then there's like a far intersection point on that back edge, right, on that back face. Well, the first one, you come in at the surface, and then you leave at the back surface. Well, you want to know what those values are, so they're passed in by reference. The T-min is the close intersection point, and T-max is the far intersection point. T0, that's equal to 0, generally, because we want to start at T equals 0, right? And that's just kind of a parameter that you can pass along. And then there's also a T1 that's like a maximum extent if you want to cut it off at a certain distance. It could be like a view distance or something on that order. I've been setting it to a high number because I'm not actually sampling densely along it anymore, so it's not a big deal if it's a big number. Basically, I'll only range through samples that are along that vector between t equals t-min and t equals t-max. So what that means is I'm only sampling inside of the cube. Okay, so only when it's relevant to sample am I sampling. Okay, so for a vector that comes through here, I have a lot more samples, but that's just because I passed through more of the block. So as I come through here, I'm going to have more samples until my exit here. But that's just because it takes a longer path through the block. So eventually, what you end up with is this filled out image that's based upon how you've hit that that block out in space. And I don't know, I think it's real neat. This really speaks to me. The shapes, being able to draw in 3 dimensions really speaks to me. I don't know, here, let's get more into the explanation of how the data is held, then we'll get into the drawing functions. So basically, we're holding colors as a struct that contains red, green, blue, and an alpha channel. Now, as you saw before, the palette is I wish the scroll function worked in the image viewer here, because it's a real pain in the ass, but okay, I actually have cursors, so we'll do that. Anyway, you don't do side to side. God. So the palette, you reference it with a state value, and that is part of this voxel struct. State holds an unsigned character value. This is not implemented right now. It's just kind of, I have it commented out. This is the mask value. So mask is a Boolean value that allows for a 3-dimensional stenciling kind of process, and I've been experimenting with that. I'll explain some of the functions that are available for that. But basically, well, we'll just get into it. This is what holds the data. The data is an array that is num cells long. That's xdim times ydim times edim. So that becomes a very long array. So now this bool mask is kept as part of the voxel structs, so that's all included there. Now, come down to the drawing functions. We'll start with the mask functions, I guess. I just kind of set up a key here. It's not that significant. So initialize the block. Okay, that deletes any existing block if data not equal to null. It's basically what that says. It's yeah. So if data is not equal to null, delete the data. You get your input values. And this is just if you want to fill it with noise. Like this one is just kind of filled with noise. I have it's just random number generation. Just making it as random as possible without any effort. It's supposed to give it a little bit of a staticky kind of look. I was using it to test the block initially, and I liked how it looked in certain pictures anyway. Yeah. By allowing it to refer back to the parent class and declare a new array for that class here, this draw function has all the functions that came out of that old Veraldo class. So I like this structure. It's kind of cool. It's the child class. It's not really a child class. It's just kind of below it in this particular structure. It refers back to a higher level class that that is instantiated in the main function. So then I go through for that length and generate a number, whatever, or fill it with a zero value. And see, I need to go through these. I'm still working on this. I just want to include this. Actually, I don't want to do it there. I want to do it. Let's go and do that. But yeah, I just want to make sure it's not masked, so it can be drawn to. And then you want to set the just random values, whatever. So now get back into some of this other here. Now clear all sets all voxels contents to state 0, and the mask value set to false. So you can draw on a blank slate there. You can unmask all voxels that set the state the mask value to false for all voxels. You can invert the mask, which means obviously any true become false and any false become true. You can mask all the non-zero values, and so that's like in the case of this here, it would mask any of these ones that are non-zero. The empty space is 0 values. Okay. So basically, and then there's mask by state. So if you wanted to just get things that are of a particular type, you can do that. So then you get into the draw functions, and each one of those has some arguments that refer to how it is drawn, and I've got that how highlighted in gold here. So those are establishing the position of a point, the ends of a line segment, the three vertexes of a triangle in three-dimensional space, the center of a sphere, and then the radius. This I need to work on just because right now it's locked to X, Y, and Z in the display, so I can't rotate it in any way, shape, or form. Need to look into some kind of representation of that shape where I can rotate it or derive something with some matrices in it. It shouldn't be too hard, but it's probably similar to what I'm doing with the rotation in the other when I was talking about in this case rotating the origin vectors. So the point, you set a value at that vector point. Now there's a couple things, and these are common to all the draw functions. Set is the integer value that you want to set for this particular voxel, okay? So that's the state, what the state value is going to get set to, okay? And that's what you're drawing, basically, the color you're drawing. Now, draw. This is added. So there's draw and mask, okay, and you generally do want to draw, right? Because you're calling the draw function. But there may be cases where you just want to mask a certain shape. So I've allowed for that by allowing you to not draw. So you can set draw to false, and you can just mask. So the so points, line segments, triangles. There's probably a better way to do triangles than I'm doing it right now. Right now I have alright, so the three vertexes of a triangle, I use that to make two vectors. There's a starting point in space and then two other points in space. Well, I step along these lines, okay, so like 1, 2, blah 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 blah, and I do the same thing over here, 1, 2, blah blah blah, okay. Well, then I go through and I draw lines, and I use the draw line segment function to draw in between these lines. So generally I make these steps small enough so that it's quite dense, and you end up with a pretty good coverage of that triangle. So it's only as good as the line segment function, but it works pretty well. There aren't any triangles in this right now, but it does work pretty well. The sphere, you can see, you actually can't see an example of it because these are all the ellipses. But you could understand that this is, you could think of a sphere in here, and that allows you to do something that's just perfectly round. Here I've done one that was extended along this axis, and then I cut one out that was extended very far out along this axis. And the same sort of thing happened here for this ground thing. Basically I masked the top half, or I don't remember exactly what the process was to mask this, but it's a sequence of instructions that allowed me to draw this using that stenciling process. This cage around here was drawn first, and then I drew the shape of this sort of car chassis. It's just kind of a demonstration object. But so the car object was defined in terms of points, and I was able to rotate those points around the car's origin, which is established to be at the center of the cube. So I'm really trying to design this as something where it could be general purpose, kind of like graphics. So if you want to define your points like that, yeah, I should include something to allow for rotation, or maybe some sort of model. I'm not sure exactly how to handle it, but we're going to look into it further. But this one was all just pretty much hard-coded points, and it was not that good. But I was able to rotate it, and so it rotates here independently of the rotation of the block, to kind of show that off. But yeah, so you've got, some sort of drive line here and some wheels and stuff. I'm working on alpha so that some parts of this can be transparent. That's going to be kind of like as you go through some of this block, as you step along here, you're going to look at your samples and you're going to say, alright, well, I've got these samples, okay, well, this one is kind of like, not very, it's like colored in, but it's not very dense. It has a low alpha value. Well, then the next one has a 0 state, okay, well, then that's, empty. So, whatever, you don't really need to consider its color. Then you get to one and it's solid. Okay, so it's colored all the way in. Well, your alpha value goes above a threshold. I think it's just going to be 1, the value of 1. So you're summing until you get to 1. Because this is lower, it didn't go above the threshold. You added 0, it didn't get above the threshold. And then you get to something here, it's above the threshold, you stop. Then you look at an averaging process where this is averaged with the lowest weight because it's got the lowest value. This is averaged, this is averaged with a weight based on its value of alpha. This is averaged with a weight based on its value of alpha, which being 0 would not give a contribution. So this fully shaded one has a weight based on its weight here, and then you derive your RGB values for the output pixel back at the screen here, based upon some kind of averaging here, and specifics of implementation there are going to be a little bit more involved in that, but that's kind of the gist of it. Let's see. Yeah, so spheres, ellipsoids, cylinders are basically you establish a bottom point and a top point, and you can rotate that in three-dimensional space. They can be vertical, they can be sideways, they can be up, down, left, right, whatever. There's an extension to that. You look at a radius there for the cylinder, and for the tube you look at an inner radius and an outer radius, so that you can have an empty tube. Quadrilateral hexahedron is this is a cube shape, but interestingly you can stretch it along any axis. You can skew it. The real issue comes up when the 4 points that make up a face stop lying in the same plane. What I mean there is that so say I have points A, B, C, and D making up a face. whatever their connection scheme is, that's kind of, it is kind of an issue right now because it's, you have to kind of look at here and see. I don't know how sensitive it is to rearrangement of those input values, but they're all established as points. And, yeah, I don't know how I feel about that. But basically, what can happen here is if these are not in the same plane, you could see something where, say for example, D comes up and is here now instead. And, now instead, you're looking at a shape that's like this, okay, and it becomes ambiguous here because now I have some deflection here between the line between these two vertexes and these two vertexes, right? There's some distance in between those lines. Well, that's where we have issues because I either, based on how this is drawn, I either am using these surfaces or I'm using the surfaces that are kind of like down this. Come back. I think GIMP's blown up. Yeah. Yeah. Alright. Anyway. So, we don't need that. Anyway, I'll just draw that again because that was not the greatest depiction of it. Basically, so I've got my shape here. I've got my 4 points. Well, things start to get ambiguous because now, am I drawing like am I drawing this outer face and this outer face, or am I doing like this one, the one that goes from this top line down, right, and then the back face here that would be along that thing there. So that, yeah, alright, GIMP is not enjoying what I'm doing to it, I guess, for some fucking reason. But in any event, yeah, this is fine. Anyway, that kind of gets the gist of what the problem is, basically. That, and the way this is implemented is it uses planes that are defined by sets of 3 of these points. So I take these 3 points, I get 2 vectors, I take a cross product to get a normal, and I look at that normal and that position, and I test the point about that plane, see if it's above or below, and then I do that here for that plane, here for that plane, here for that plane, here for that plane, again and again and again, and then I see finally whether or not it's inside of this shape. This method actually works for any convex object, but it's kind of limited if you want to do something that's not convex. Anything concave, you start to run into ambiguous cases where only some of the conditions apply, because it can't be below all of the planes at the same time, because the concavity sort of ruins that. How to show that? If, I guess, the 2-dimension representation works well there. You kind of, if your shape kind of goes like, good night. If your shape goes like this, then you're testing a plane like this, and it's testing a plane like this. The normals go this way, and like this. Well, now there are a number of ambiguous areas here, because everything above here is going to fail this plane test, okay? Anything above this plane is going to fail this plane test. So everything in this area of the shape is going to be not included there. Alright, well, same issue for this plane. Everything here is not going to be included because it fails the plane test for that particular plane, right? Because that plane continues off like this. Alright, well, so then you gotta look at this other plane now. It's the same thing as this kind of plane, so now everything like here is gonna fail the plane tests. So that's all this stuff, because this plane comes down. So that's where concavity becomes an issue, because like that. Whereas if you're all inside, you know, you're just inside the block. It's no big deal, and all these plane tests can go positively. You don't violate any of them, they're all positive, they all return a true value, okay? And that's basically just based on the yeah, I have it written somewhere. Yeah, so this is the equation of a plane. And then I do it just like that. Test the test point against the plane's equation, and I return a result, true or false. False if the point is above the plane, up here. True if the point is below the plane, down here, inside. Okay. So by doing that 12 times, we're able to establish that hexahedronical shape, if you will. It's a cube, but it can be warped, it can be stretched, it can have faces that are not square or rectangular. And if you don't care about weird artifacts, you can give it ambiguous cases where these aren't in a plane. Basically, what I'm trying to say is, since you have these 4 points, you're only considering 2 groups of 3. I don't remember which sets they are. I have it all coded out, but basically, well, let me show you an example of it. It's this block here. It's a an engine block or something, but it tapers as it comes down. And yeah, so the potential for that is a lot greater than something that's axis aligned. Initially, I was doing it the same way I was defining this block. I was saying like a minimum index and a maximum index, and then you're kind of just like going along the x, y, and z between those extents. So, yeah, this is the current imagining of the voxel renderer. I think it's got a lot of potential. I'm doing some documentation so I can get back into it and understand it. Really setting it up so I can keep myself working on it. One of the big things is like maintaining momentum, I think, on some level. Being able to reassure myself that I know what I'm doing with it. In any event, we've got quite a bit left to do. Like I said, all these are kind of empty right now. I have them all on my GitHub right now for version 4. They're all implemented. I just have to convert them because like for example, yeah, like these refer to an old representation of, well, actually this one I could take directly because it calls drawline segment, but that's the exception rather than the rule. Or yeah, go ahead and make a liar out of me, why don't you? Anyway, this was something stupid I was doing, and I just needed some time away from it to get away from that, because this was this really stupid scheme that was just, it had 2 steps and it was really dumb. I don't know what the hell I was thinking. It's one of those things where when you figure it out, it's so fucking simple. I just have an array of these, so I use this state to reference where in the array I want to get, so I have RGBA palette. I just reference that array with the state value, and then I can get the RGBA value out of it. So, stupid, but it's good, I think, for right now. So this mask value, I want to see if I can use bits for that, because I know a mask, or the bool uses a integer or something like that. I don't know. I'm not sure if that's even really significant, or if the compiler does that anyway. The lighting intensity thing is going to be based on the display function. Well, I guess I lost that one, but in the way where there's the sphere, and you have the kind of like thing here that's pointing into the sphere, or you have your block inside the sphere. Well, damn, dude. Anyway, so we're gonna do the same sort of thing, except same sort of thing, except as we step along these, we're gonna apply a lighting value to them as we step along the vector that goes through the cube. And I'm not sure exactly how we're gonna implement it, but that's about as far as I am with it. I also want to do an ambient occlusion thing that's based on the number of non-zero state neighbors, and it might have something to do with the alpha values. I don't really know. We'll have to figure that out as I get to that. But yeah, so I've got a little bit of documentation in here. I don't know, you can take a look at that, I guess. Like I said, display function isn't even written at all. I have it on GitHub. It's I just haven't copied it back over. Trying to think if there's another one that has any good pictures. No. See, I had done this renderer that was done in screen space. Basically, had X, Y, and Z defined, and then I kind of stepped along them in screen space, and then wrote to that pixel, which was kind of dumb. I mean, it's kind of rigid, and it's imagining. Anyway, this one's a lot more interesting, I think. And allows for rotation by swinging around to any point on that sphere, right? So like I said, you start at the center and you move back along that view vector. You do a negative times the t value up to the origin point. Well, you can scale that. You can move further back, then, like I said earlier, this had a whole rotation process at the beginning, so that's what moves you along this ring or whatever. You could go up or down if you wanted to, yeah, I don't know. It'd be interesting to experiment with that, but pretty much as far as I've gone with it is what's in that video. Yeah, where I just kind of scroll around the cube. Yeah, I think it's fascinating. I really like how isometric it is, sort of, from some views. Then I don't know. It has a real certain quality I like a lot. I want to continue with this. I want to add ambient occlusion, like I said, based on the number of occupied cells. So that's the number of neighboring voxel structs that have a non-zero state value. That'll be pretty trivial to include with the display function. We'll just have another flag that gets set or something. I'll have to look at how I want to do that, if that's going to be an argument or what. But yeah, so it'll just reference the array more when you're actually, so you sample through. Yeah, it won't be hard. You sample through the block, and so as you get to any particular grid index, so you're inside of this one here. Well, then you're going to sample this one, 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 and it's going to get darker as more of these are occupied. Right, so you just kind of scale the RGB values based on how many of these are occupied with non-zero state values. So say these are 0, then they don't count towards it. In three-dimensional space, you're looking at a neighborhood that contains 27 cells. Because it's, well, if you think about it in 2 dimensions, it makes a lot of sense. You've got -1 on each dimension, you've got 0 on each dimension, and you have +1 on each dimension. Kind of ternary logic, sort of. Interesting. I actually didn't think about the fact that it is ternary logic there. Anyway, we're not going down that rabbit hole. This is 2-dimensional here, so you have -1 here, and 0, and +1. Then the the equivalent is done in 3 dimensions to get 27 cells, including the center one. Yeah, so I haven't done that yet, but I will. Yeah, so this is pretty much the gist of it. It's coming right along. I'm experimenting with a lot of stuff from C++ 2011, which I know is already old, but I learned 98, and I learned C++ 98 in 2013 or 2014. So I figure I might as well catch up with things, figure out what the hell's going on, I guess, and this is kind of a good way to do that. Yeah, that's about all we got here. I'll probably be doing some more videos of these, just to kind of walk through what's happening with it, basically. So I appreciate checking this out or whatever. Yeah, I'll definitely put up more videos here on this channel if you're curious in seeing that. This actually shows the optimization that I did here. The pink ones are the ones that go through empty space. The pink cells. Those are the ones that are sampled along inside. Because everything black here on the outside is just misses the cube entirely. So we don't even do any real vector stuff for this stuff. Anything out here, just ignore it. What I think is interesting out of this is that you get a few artifacts along here that are, and I'm not sure exactly what that is, but you do get some that are sampling through empty space where there is no empty space. This is all the way populated to the edge, but it somehow got a 0 value, and I'm not sure. Whatever. That's not as significant, but I don't know. That's where we're at with everything.